Hello everyone, welcome to my third lecture video. I think all of you have watched my first two lecture videos, and watching them I think you have all started doing homework number 8. Today we'll do the remaining part of test 3, that is we will try to cover the materials for homework 9. So at the end of today's lecture you should be well prepared for test 3. I'll put one more lecture video which will be exclusively dealing with some reviews for test 3. So I think all of you have got my email that test 3 has been rescheduled to next Monday, that is April 6th. So today we will cover mainly the remaining three remaining topics which were there in test 3. So these three topics were, so our plan for today will be first of all we will study properties of definite integral, then we will study geometric interpretation of definite integral, then we will study the fundamental theorem of calculus. So these are the three remaining topics which were left, we will cover today. Okay, so let's start with properties of definite integral. So there are some properties of definite integral which are very handy in doing some calculations. So we will study them and then apply them to solve some problems. So the first property of definite integral which is very handy is this, property 1. If A, B and C are three numbers such that A is less than B is less than C, then integral from A to C fx dx can be written as integral from A to B fx dx plus integral from B to C fx dx. This is the first important property of a definite integral. So if I have three numbers a, b, c which satisfies A is less than B is less than C, then integrating from the point A to the point C is same as first integrating from A to B, then integrating from B to C and adding these two integral sum. So this is the first important property of definite integral which will be handy in doing a lot of problems. So if we have three numbers a, b, c, integration from A to C fx dx is the same as, we can break it first from A to B then plus from B to C. Okay, so this is the first important property of definite integral. Now let's study the second important property of definite integral. So property 2. Okay, so the property 2 is if fx is an odd function, so I think all of you know what an odd function is. That is f of minus x is minus of fx. If fx is an odd function, then for any number a, if I take any number a, then if I integrate from minus a to a, that odd function, this is always 0. So this is a very important property that if fx is an odd function, right, that is if f of minus x is minus of fx, then if I integrate that odd function from minus a to a, where a can be any number, so one number and just its negative, if these are the two limits of integration, then the value of the integral will be always 0. So what happens if fx is an even function? We have a similar result. If fx is an even function, that is f of minus x is just fx. If fx is an even function, then I can write this integral from minus a to a fx dx. This can be written as 2 times integral from 0 to a fx dx. Right? So if fx is an even function, then we have a slight modification. In the odd function case, the result was 0. And in the even function case, I can write down integral from minus a to a fx dx as 2 times integral from 0 to a fx dx. So this is the difference, what happens in case of an even function. So if I have an even function, then integral from minus a to a fx dx is 2 times integral from 0 to a fx dx. Okay, and in case of an odd function, this result is 0. So this is the second important property of a definite integral. The third important property is property 3. So if fx is defined in an interval AB, and if small m and capital M are respectively the absolute minimum and absolute maximum of fx in AB, then integral from a to b fx dx satisfies small m times b minus a is less than integral from a to b fx dx is less than capital M times B minus A. I advise you to keep your notes, that is note 8, with you when you listen to these lectures. So if this is property 3, so if I have a function which is defined in the interval AB, right, and if I know that small m and capital M, these are respectively the absolute minimum and the absolute maximum of the function fx in this interval AB, then I can write down that this integral will satisfy this inequality, that the value of this integral will lie between that absolute minimum times b minus a and absolute maximum times b minus a. So I think all of you know from our knowledge what we have gained from the course of test 2, that if we are given a function and if we are given an interval, how to find out the absolute minimum and the absolute maximum. Just let me repeat. So what you do is that you compute out the derivative of this function, then you equate that derivative to 0, then you solve for x. The values that you get are the critical points, then you find out the value of the function at the critical points and at the two boundary points a and b. The largest among these values gives you the absolute maximum, that is capital M, and the smallest among these values gives you the absolute minimum, that is small m. Now once you find out capital M and small m using the technique that I just told you, then you can write down this inequality, that the value of this integral from a to b fx dx must lie between small m b minus a and capital M b minus a. Now why is this property important? This is because the value of all integrals cannot be calculated. So whatever functions that I'll give you or will appear in your tests, all of them can be easily computed, but there exists functions fx in nature such that the value of this definite integral cannot be easily computed. In fact, there are functions which are not integrable. Integrable means for those functions this value cannot be obtained definitely, or we cannot obtain this in a closed form. For such functions for whom we cannot directly compute out the value of this definite integral, this inequality plays an important role. This inequality at least tells us, okay, whatever may be this value, it will lie between this and this. So we have a rough estimate of the value of this integral from this inequality. So for functions for whom we cannot find out the integral, this inequality gives us a rough estimate of what the value is. We can say that, okay, whatever may be the value, it will always lie, it cannot be smaller than small m times b minus a, also it cannot be larger than capital M times b minus a. For such complicated functions, this inequality becomes very handy, and that is why this property is very important. So if, those who have majors in engineering or applied sciences like physics, chemistry and so on, economics, you will encounter functions which are not integrable, that is you cannot find out directly the value of this integral using the techniques that we will study. But for all such functions, if you can derivative you can always compute out, and computing out the derivative and computing out the absolute maximum and the absolute minimum, you can always find these two numbers, and from these two numbers you can always estimate an upper bound and a lower bound for the value of this integral. That's why this property is so important. Now we have studied these three properties. Now we will apply these three properties to do problems. So let's take the first problem. So problem number 1. It is well known that it is well known that integral from 0 to 10 fx dx is 17 and integral from 0 to 8 fx dx is 12. Find integral from 8 to 10 fx dx. So this is your problem. So you are given the value of integral from 0 to 10 fx dx. You are also given the value of integral from 0 to 8 fx dx. So you need to find out, let me write this down below so that you have no difficulty in viewing it. Then what you need to find out is this. Find integral from 8 to 10 fx dx. So you are given the value of this, the value of integral from 0 to 10 fx dx. This is equal to 17. So the value of this integral is 17, the value of this integral is 12, and we need to find out this. So how do you do it? So first, for doing this, observe that we will use property number 1. Observe that these three numbers 0, 8 and 10, if we put them on the number line, they lie first 0, then 8, then 10. That is 0 is less than 8 is less than 10. So by property 1, that we have just studied, we can write integral from 0 to 10 fx dx as integral from 0 to 8 fx dx plus integral from 8 to 10 fx dx. We can do it, write it. So we can write down integral from 0 to 10 fx dx, right, is the same as, first I integrate from 0 to 8. So instead of integrating from 0 to 10, I can first integrate from 0 to 8, then from 8 to 10, and then add them up. Now you see that we already know what is the value of integral from 0 to 10 fx dx. It is given to us, so it is 17. The value of integral from 0 to 8 fx dx, it is also given, it is 12. So we are just left with this. So clearly we can subtract 12 from both sides. So we get integral from 8 to 10 fx dx is 17 minus 12, which is 5. Thus, then that's what we were asked to find out. We were asked to find out the integral from 8 to 10 fx dx. So integral from 8 to 10 fx dx is 17 minus 12, which is 5. That's it. Extremely easy. So now let's take the next problem, the second problem. So problem 2. So problem 2 is evaluate integral from minus 1 to 1 10x whole divided by 1 plus x square plus x to the power 4 dx. This is your second problem. So how to find this out? So to find this out, you see that you are given a definite integral and it's very complicated. You see that it has tan x 1 plus x squared. So whenever you are given a definite integral in which you see whatever is the upper limit, you look at the upper limit and you look at the lower limits. They are just inverse of each other. If it is 1, it is minus 1. So if you see in a definite integral, the upper and the lower limits, they are just negative of one another, then you will understand that we have to do this problem using property 2, right? That's the only thing we need to do here. So we need to just check whether this function is an odd function, and once we check that this function is an odd function, then we can use property 2, which states that if I have an odd function and if my limits are such that one is the negative of the other, the value of the definite integral is 0. So if you have a problem in which the limits are just negative of one another, check whether this function is odd or not. So let's check. So let fx equals to tan x divided by 1 plus x squared plus x to the power 4. So let's take f of minus x. So I have tan of minus x 4 divided by 1 plus minus x whole square plus minus x whole to the power 4, right? So we have to find out the value of tan of minus x. So what is tan of minus x? Let's try to do it in graph here. So tan of minus x means sine of minus x divided by cosine of minus x, right? Sine of minus x is minus sine x. This is a property from trigonometry. You can just learn it right now. Sine of minus x is always minus sine x, and cosine of minus x, it is always cosine x. This is a very known formulas in trigonometry. It's very well known that sine of minus x is minus sine x and cosine of minus x is just cosine x. So cosine of minus x will be just cosine x. So you get minus sine x by cosine x, which is minus tan x. So you have tan of minus x is minus tan x, right? So here, instead of, in place of tan of minus x, I can just write down minus tan x, and since my powers are even, so it will become 1 plus x squared plus x to the power 4. So what do I get? I get minus tan x by 1 plus x squared plus x to the power 4, and this is just fx, so it will be just minus of fx. So f of minus x is minus of fx. That means what? This function is an odd function. So fx is an odd function, and it's an odd function means what? The value of this integral will be 0. Therefore, since this is an odd function, by property 2, the value of integral from minus 1 to 1 tan x by 1 plus x squared x to the power 4 will be 0. Now let's take the next problem. Property 3. Problem 3. without evaluating the integral from 1 to 4 square root of x dx approximate an upper and lower bound for the value of the integral. Okay, so without evaluating the integral 1 to 4 square root of x dx approximate an upper and lower bound for the value of the integral. For this, so for using property 3, we have to first of all find out what the function is and what is the domain in which the function is defined. So here the function is fx equals to square root of x, and the domain is a is 1 and b is 4. So for utilizing property 3, we have to first find out the absolute maximum or absolute minimum of this function in the interval 1 to 4. So for this, I first compute out the derivative of the function fx. So f prime x is what? This is dt x of square root of x by power rule. This is ddx of x square root of x means x to the power half. So by power rule it will be half x half minus 1. So half x minus half, that is 1 by 2 square root of x. Right? Now, so f prime x is 1 by 2 square root of x. So equating denominator to 0. Or how do we find out the critical points? We find out the critical points by equating the numerator and denominator of the fraction. Here in the numerator I have nothing, in the denominator I have 2 square root of x. So equating the denominator to 0, I get 2 square root of x equals to 0. Solving, I get x equals to 0. So x equals to 0 is the critical point. Right? Now, once I find out the critical points, I will find out the value of the function fx at the critical point and at the two boundary points. So I will find out f of 0, I will find out f of 1, I will find out f of 4. So let's compute out. F of 0 will be square root of 0 equal to 0. If I put 1 here, I get square root of 1 equal to 1. If I put 4 here, I get square root of 4, which is 2. So I found out f of 0, f of 1. So out of these three values, what is the value in which my value is maximum? So clearly this is the maximum and this is the minimum value. So clearly 0 is the absolute minimum and 2 is the absolute maximum. So here small m is 0 and capital M is 2. So by property 3, I can write small m times b minus a is less than integral a to b fx dx is less than capital M times b minus a. So just plug in the values. In place of m just put 0, in place of b just put 4, in place of a put 1, in place I get 1 to 4, fx is square root of x dx is less than capital M is 2, 4 minus 1, so I get 0 less than 1 to 4 square root of x dx is less than 2 times 3, so 0 is less than 1 to 4 square root of x dx is less than 6. So the value of this integral lies between 0 and 6. 2 times 3 is 6. So my two bounds, so the two bounds I can write down. So the upper bound is 6. The upper bound is 6, right? And this is the upper bound, and this is the lower bound, 0, and the lower bound is 0. Right, so this is, so from here you get the upper bound is 6 and the lower bound is 0. So this brings us to the end of our first topic today. Now we will start geometric interpretation of definite integrals. Geometric interpretation of definite integral. So I have two cases here. First of all, I consider the case when the function is always positive, that is fx is greater than 0 in the interval a. So I am drawing the figure here. This is my fx, this is my interval ab. So if my function is always positive, that is in this interval it always lies above the x-axis. So this is my x-axis, x o x prime, y o y prime. If my curve always lies above the x-axis, then this integral from a to b fx dx, it represents this area A. So what is this area? This is the area bounded by the curve y equals to fx, x equals to a, x equals to b, and the x-axis. This is very important, x-axis. So if I integrate a function fx from a to b, and if the function fx always lies above the x-axis, this integral, the value of this integral gives me the area bounded by the curve y equals to fx, the lines x equals to a, this is the line x equals to a, this is the line x equals to b, and the x-axis, not the y-axis, remember the x-axis, it gives me the area bounded by the curve and the x-axis. This is very important. So I have underlined this x-axis. So because why it is x-axis, because I am doing dx. If I will be doing dy, it will be y-axis. Okay, so if I integrate from a to b fx dx, I get the area bounded by the curve y equals to fx, the lines x equals to b, the x-axis, that is this area. Now let's consider the case when the function is sometimes positive, sometimes negative. So case 2. Right? So the function is sometimes positive, sometimes negative. So this is an example of such a curve. So the function y equals to fx in the interval AC, this function is positive, that is it lies above x-axis. In the interval CB, this function is negative, that is it lies below the x-axis. In such a case, so I have two areas, right? One I am showing by dots, and the other by lines. Okay, so let us call this area as A1 and let's call this area as A2. So if my curve, some part of my curve lies above the x-axis and sometimes below, now if I integrate the function from a to b fx dx, what do I get? The value of this integral will actually be a1 minus a2. Right? That is, what is a1? a1 is the area above the x-axis and a2 is the area below the x-axis. Okay, so if some part of the curve lies above the x-axis and some part below, if I integrate the function from a to b, I'll get the difference of these two areas. So the area above the x-axis, that is this area, minus the area below the x-axis, which is a2. Now why do I do difference? Because I think if you remember that this area is negative. So in order to make this area positive, we are putting a minus sign. So this is very crucial, you have to remember, if some part lies above, some part lies below, it will be area above minus area below. Now let's do some problems on this geometrical picture. So problem, use definite integral, to find out the area of the region that lies under the curve y equals to x square root of x in the interval 0 to 4. So this is your problem. So you are given a function and you are given an integral. You have to find out what is the area of the region that lies under the curve y equal to x square root of x in this interval. So observe that this function, whatever value of x you take in the interval 0 to 4, this function is always positive. So this curve lies above the x-axis. If you draw the curve of this function, so this is y x square root of x and this is my interval 0 to 4. Right? So this function in the interval 0 to 4, you can choose any value of x between 0 to 4, choose 1, 2, 3, 4, and just put in this function. You will see that you will always get a positive value. What does that mean? This curve lies above the x-axis. This is x-axis, this is y. So what is my aim? My aim is to find out this area. Because the problem is, what is the problem? Just understand the problem. The problem is, use definite integral to find out the area of the region that lies under the curve. And that means I need to find out this area. So just what we have studied, how to find out this area if the curve lies entirely above the x-axis. Just integrate this function from 0 to 4. So required area equal to simply integral from 0 to 4 what this function x square root of x dx. So this is a definite integral. How do I find out? From our lecture video 2, I first of all ignore these limits and just compute out the indefinite integral, then just find out the difference, the values. So first I ignore the limits 0 and 4 and just consider this x square root of x dx. This is x times x power half dx, so this will be x power 3 over 2 dx, right? 1 plus half, this gives you 3 over 2. Now if I evaluate the corresponding indefinite integral, I get x 3 over 2 plus 1 by 3 over 2 plus 1. This is x 5 over 2 by 5 over 2. This is 2 over 5 x 5 over 2. This is the value of the indefinite integral. Now how do I find out the area? Just once I find out the indefinite integral, I plug in this expression 4, then I put 0 and find out the difference. So therefore required area first put 0 in that from first put 4 in place of x, so it will be 4 to the power 5 by 2, then put 0, 2 by 5, 0 to the power 5 by 2, right? So this is equal to 2 by 5, 4 to the power 5 by 2, so that means it will be 32. You can use a calculator. So it will be simply 64 by 5, and if you use a calculator you can easily find out the exact value. Now let's do the second problem. Use definite integral to find out the area bounded by the y-axis. This is little bit tricky. Let's consider the next problem. And problem 2 is this. Use definite integral to find out the area bounded by y-axis, the line y equals to 1 and the curve y equals to 4th root of x. This is my problem. So use definite integral to find out the area bounded by the y-axis, this line and this curve. So let's try to draw this particular line, this curve first. Let's try to draw a rough sketch of this graph. Right, so this is my function y equals to 4th root of x. So the best way is to do like this. Take a value of x, y in order to draw a graph. Take a value of x. If I take x equals to 0, the value of y I get is 0, right? If I take value x 1, 4th root of 1 will be also 1, right? So if I take right, so how to draw the graph? At 0 it will be 0, at x equals to 1 its value will also be 1, right? The curve will be like this, because from this table if I put x equals to 0 I get 0, if I put x equals to 1 I get 1. So this is how the curve y equals to 4th root of x looks like. Now I have to find out this area. See, use definite integral to find out the area bounded by the y-axis, right? Y-axis, the line y equals to 1 and this curve. That means basically I need to find out this area. This is my required area. So let me do it nicely. This is my line x equals to 1. This is x equals to 1. And I need to find out this area, right? And this is y equals to 1. And this is the curve y equals to 4 root of x. So this is the area I need to find out, the area bounded by the y-axis, the line y equals to 1 and this function. Now there is a problem here. The problem is as follows. So though I need to find out this area, but if I integrate this function from, that is y equals to 4th root of x, from 0 to 1, will I get this area? No. As I told you when I defined what is the geometrical meaning of a definite integral, I told you if I integrate this function y equals to 4th root of x from 0 to 1, I will get this area, not that. That means I will get this dotted area. I always get the area bounded by the x-axis, not the y-axis. So if I integrate this function y equals to 4th root of x from 0 to 1, I will get this dotted area, not the area I need to find out. So what do? But I observe that this whole thing is a rectangle, right? This whole thing is a rectangle. Now since this whole thing is a rectangle, let's name this rectangle. Let's call this as A, let's call this as B, let's call this as C, and let's call this is already O. Origin is O, right? So in this whole rectangle, you see the area of this segment ABO plus area of OBC. This together gives you the area of the rectangle. Now area of rectangle ABCO will be equal to, here the length is 1 and the width is also 1. So 1 times 1 is 1. So the area of this rectangle is 1. And what is the area of this dotted line? I can find out the area of this dotted area just by integrating the function 4th root of x from 0 to 1, and area of the dotted part, that is OBC, is just, if I integrate this function from 0 to 1, 0 to 1 4th root of x dx. So let's find it out. Let's compute out this integral. So first we forget the limits and compute out 4th root of x dx. So 4th root of x means x to the power 1/4 dx. So by the laws it will be x to the power 1/4 plus 1 by 1/4 plus 1. So it will be x to the power 5 by 4 by 5 by 4. So I get 4 by 5 x to the power 5 by 4 dx. Now if I want to find out this dotted area, now in this expression first I put the top value 1, then I put the bottom value 0 and find out the difference. So this one will be just putting 1 in place of x. I get 4 by 5, 1 to the power 5 by 4, then I put 0, I get 4 by 5, 0 to the power 5 by 4. So I get 4 by 5 as my answer. The value of this integral 0 to 1 4th root of x dx is 4 by 5. So 4 by 5 is this dotted area, or the area of OBC. But what I need this lined area, right? I need the area of ABO, because that is the area bounded by the y-axis, the line y equals to 1, and this curve. So required area that is area of ABO will just be the total area, the area of the rectangle, which is 1, the whole area which is 1, minus the area of the dotted part, which is 4 over 5. So 1 minus 4 over 5 just gives me 1 over 5. So 1 over 5 is my required area, which is bounded by the y-axis. This is the line y equals to 1 and the curve. This problem is very, very important. Now we are doing the last topic for test 3, that is a very, very important topic, which is the fundamental theorem of calculus. So as the name suggests, this is a very, very important result. It's the fundamental theorem of calculus. Fundamental theorem of calculus. So what is the fundamental theorem of calculus? The fundamental theorem of calculus states that if fx is continuous in a given interval AB, so if a function is there and it is continuous in a given interval AB, so continuous means its graph has no breaks in it, then the function, then gx, if I integrate from a to x ft dt, I define a function in this way. I integrate the original function from a to x, I get a function gx. So let me try to draw using figure. What do I mean? Suppose the function fx is continuous in interval AB. So that means what? The function, the graph of that function has no breaks in it. This is my fx and this is my AB. So this is my function fx, right? And this is my interval AB, so a function is continuous. Then I define this function gx. What is this function? It from a to x ft dt. Now what we have already studied, what does this integral represent? A to x ft dt, this represents the area from a to x. So let's take a point x here. So this area will be my gx. So this area is gx. Let me use dotted line point to denote this. Right? So if I have a function fx, right, and then if I just take a point x here, and then if I find out this area will be gx, right? So because we are integrating the function ft from a to x, so this is this area. So I define a function gx which is defined by from a to x ft dt, that is simply this area, integral of this function from a to x. Then this function will be such that this function will be the antiderivative of fx. Right. So what does this mean? That gx is the antiderivative of fx. This means that is, if I compute out the derivative of g, that is g prime x, I get fx. So this is the fundamental theorem of calculus. So if a function fx is continuous in this interval, then if I form a function gx in this way, what is gx? Gx is integral from a to x ft dt. That is, if I take a point x in between a and b, and if I compute out this area from a to x, that is, and denote this area by gx, then this function gx, it will be a function. If I take the derivative of gx, I will get back fx. So this is the fundamental theorem of calculus. Now let's try to understand it more deeply. So what does this mean? G prime x means what? Gx is this, so g prime x means ddx of gx. So ddx of gx is fx, and gx is this. That means what? ddx of integral from a to x ft dt is fx. So observe this function, this expression very, very clearly. So here I am integrating from a to x ft dt, and after that I am differentiating again. So if I take a function and first integrate it from a to x, and then if I differentiate it, I will get back the original function. So this expression tells me, this gives me a solid proof that differentiation and integration, they are reverse processes of each other. if I take any function ft, first integrate it from a to x, then if I differentiate it, I'll get back the original function. So take a function, first integrate it, then differentiate it, I get back the original function. So the fundamental theorem of calculus in a way tells you that differentiation and integration are reverse processes of each other. With this expression, take a function, integrate it, then differentiate it, get back the original function. And if we want to geometrically understand what the fundamental theorem of calculus is, take a function fx defined in the interval ab, then take a point x between a and b, then you compute out the area of this strip, this whole thing, this whole strip, and denote this area by gx. Gx is integral from a to x ft dt, that is the area bounded by this function in the interval a to x. Then if you denote this area by gx, if you take the derivative of this area, that is the derivative of this function, you get back the original function fx. So this is the fundamental theorem of calculus, and now we will apply this fundamental theorem of calculus to solve different problems. Okay, so let's take the first problem, which is very important. So a graph is given to you. I'm drawing the graph. So this is the graph of a given function y equals to fx, right? And you are we define an expression. We define gx as integral from 0 to x ft dt, right? So this is my function. So this is a given function. This is the graph of a given function y equals to fx. This is the graph, and the shaded is the area which is bounded by this function at the x-axis. You see that this function y equals to fx, some part lies above the x-axis and some part below. From 0 to 3, this function lies above x-axis, and after from 3 to 7, this function lies below the x-axis. Now you define a new function gx, which is the area from 0 to x, that is the area. Now you need to find out, first of all, a few things. Your first thing is you need to find out g of 0. Okay. You need to find out g of 0. So what is g of 0? So put g, if g of x is integral from 0 to x ft dt, g of 0 will be integral from 0 to 0 f of t dt. Now remember, if the two limits of in an integral are the same, then the value of this integral will be 0. So this is your g of 0. Now let's find out g of 2. So what is g of 2? So put in place of x2, so you get integral from 0 to 2 ft dt. So what is the meaning of this thing? So you are integrating the function ft from 0 till 2. So what this means, look at this graph. So here is 0 and here is 2. So basically you need to find out the area from 0 to 2 under the curve y equals to fx. So you draw a line here. So basically you need to find out this area, right? So you can name this area. You can name this as, this is origin O. You can name this point as B. You can name this point as B, right? And you can name this point as C. You can name this point as D. You can name this point as E. You can name this point as F. You can name this point as G. You can also draw this, right? And you can name this point as G, right? So I have named different points here. So let me zoom this for you. Right, so I have named this point as A, this point as B, this point as G, this point as F, this point as C, this point as G, this point as E, right? So my integral from 0 to 2 ft dt will be this area. Now you see that this area actually consists of a rectangle and a triangle, right? So this is the rectangle which I am shading here. This is the rectangle, and this is the top triangle, right? So what is the area of this rectangle? You see that its length is 2 and its width is also 2, right? So the area of the rectangle, and let's name this rectangle A, G, E, and let's so we have already used, let's A, B, C. So this rectangle is ADEG, right, plus the area of the top triangle CBD. Right, now what is the area of this rectangle? Its length is also 2 and its width is also 2, right? So its area will be then length times width, it will be 2 times 2. Now the area of this triangle, the area of this triangle, so you know that the area of a triangle is half times its base times its height. So what is the base? This is the base. This is the base of this triangle, and this is the height of this triangle, right? Now what is the base of this triangle? It's 1 and it's 2. So its base is 1. So half times its base is 1 and its height. What is its height? Look at clearly. It runs from here to here. So its height is 1, 2, 3, and it's 1, 2, 3. So it should end till 5. So it's 1, 2, 3. This point is 5. So it's 1, 2, and 3. So its height is 3. So first of all, this rectangle, its length is 2 and its width is 2. So length times width plus the area of this triangle, its base is 1 and its height is 3. So half its base times its height. If you compute out, you get 4 plus 3 over 2. You add them, you get 8 plus 3 over 2. You get 11 over 2. So this is my G of 2. In the same way, I can find out G of 3. So what will be G of 3? So G of 3 will be, you see that, what is G of 3? It will be this area. 3 is this. So it will be the whole area up to the point 3. That is this whole thing. Right? So we have to add G2. G2 is up this area and G3 is plus, we have an additional triangle here. Right? So G3 will be G2 plus the area of this additional triangle CED. Now what is the area of this triangle CED? Its base is 1 and its height is 1, 2, 3, 4, 5 and 6. So its base is 1 and its height is 6. So it will be G of 2 plus 3, which is G of 2 is 11 over 2 plus 3. So 11 plus 6 over 2. So I get 17 over 2. This is G of 3. So G of 3 means area up to this 1, 2 and 3. So this is 3, right? So this whole area from 0 to 3, this whole area. The area bounded by the curve y equals to fx and the x-axis from 0 to 3. This is G of 3. So I can split it up into from 0 to 2 plus 2 to 3. So 0 to 2 means G2, you have already computed this out, plus the area of this additional triangle C, E and D, this one. Now this triangle, its base is 1 and its height is this whole thing from 0 to 5, right? So it's 1, 2, 3, 4, 5. So it should be 5 actually. Its height should be 5. So it should be 5 over 2. So it should be 16 over 2. So it should be 8. So G3 is 8 because its height is 5 from 0 till 5. So you get the value of G of 3 here. Now finally you have to find out the value of G of 6. So how do you calculate G of 6? So G of 6 means what? So we have 6 some part above x-axis and some part below x-axis. So remember that we have to do area above minus area below. So here, so this is g of 6. The g of 6 means area till this. So this is the area. So let's name this. Let it be D E F G H. Let's name it I J K L. Right. So g of 6 means this area minus this area till 6. The area of D I J K L L K L. So g of 6 will be g of 3 minus area of D I J K L. Right? Now g of 3 is 8 and area of D I J K L can be divided into one triangle and a rectangle. So this is the area of rectangle IJKL plus area of triangle DIL. So this is the area of this rectangle IJKL plus the area of this triangle DIL. So the area of this thing DIJKL, it can be divided into the area of this triangle plus the area of this rectangle. Now what is the area of this triangle? Its base is from 3 to 5, that's 2, and its height is 2. So what is the area of this rectangle? Its length is 1 and its width is 2. So it will be 1 times 2 plus the area of DIL. Its base will be 2 half and its height will be also 2. So ultimately I get 8 minus 2 plus 1. So 8 minus 3, I get 5 as my area. So in this way I get 5 as my area. This is area G3 minus area of DIJKL. So area of the rectangle plus area of the triangle. So 8 minus 3 will be 5. You should keep your notes with you so that it becomes easier for you to understand. The notes and the solutions. Because I have solved this in the notes also, so that you can match. Keep your notes side by side, listen to this video, have the questions, you'll understand everything. Now let's do the second part. It is asked, where is this function gx? My second question is this: where is this function increasing and where is this function decreasing? That's my second problem. So to do this, so the B is find, this is the second problem, find the intervals, where the function g is increasing and decreasing. So this is my function g. Gx is integral from 0 to x ft dt. So g prime x. So to find out where the function g is increasing and decreasing, I need to compute out the derivative of g. That's how we do it. If we are given any function and we are asked where is that function increasing, where function is decreasing, what do? We compute out the derivative of that function and check where the derivative is positive and where the derivative is negative. If the derivative is positive, what does this mean? That the function is increasing there. If the derivative is negative, it means that the function is decreasing there. So to find out where the function g is increasing and decreasing, we have to compute out the derivative of g and check where this derivative is positive and where the derivative is negative. Now where is the original function g? The original function gx is 0x ft dt. So its derivative g prime x will be d dx of integral from 0 to x ft dt. Right? Now, so I have to find out the value of this. Now you see that I am integrating the function ft from 0 to x, right? Then I am again differentiating it. So first I am performing integration, then I am performing differentiation. We have just studied that differentiation and integration are reverse processes, and by the fundamental theorem calculus, so if I first integrate then differentiate, this integral and this differentiation sign, they will cancel each other. The integral sign and the differentiation sign, they will cancel each other, and I'll be left with the original function. So the answer will be just fx. So the value of the derivative of the function gx is fx. So g prime x greater than 0 implies fx is greater than 0. So when is the derivative is positive? When the function is positive. And where is the function positive? You see that means where does the function is positive means fx lies above x-axis. Where does the function lies above x-axis? In the interval 0 to 3, x, that is x lies in 0, 3. So when x lies in 0, 3, the function lies above x-axis. So the derivative of the function g is positive in the interval 0 to 3. So we'll write, so gx is increasing in 0 to 3. Now the next part is, where is the function decreasing? To find out where is this function decreasing, we have to find out where g prime x is less than 0. So g prime x less than 0 means we have already found out that g prime x is fx. So g prime x less than 0 means fx is less than 0, and fx less than 0 means fx lies below x-axis, right? So where does fx lies below x-axis? This is the graph of the function fx. Fx lies below x-axis in this interval from 3 to 7. In this interval, the function lies below x-axis. So fx lies below x-axis means x lies in the interval 3 to 7. Right? So combining, I can say that my function g is increasing in 0 to 3 and decreasing from 3 to 7. So gx is increasing in 0 to 3 and decreasing in from 3 to 7. right? So my function g, it is increasing in from 0 to 3 because the graph of the function lies above x-axis in 0 to 3. From 3 to 7 the function g is decreasing because the graph of x lies below, right? So gx is increasing in 0 to 3 and decreasing in 3 to 7. Now, so just let me repeat again. My problem was this: find the intervals where the function is increasing and decreasing. To find out where the function g is increasing and decreasing, we have to compute out the derivative of g. Since gx is integral from 0 to x ft dt, so g prime x by the fundamental theorem of calculus will be just fx. So g prime x positive means fx positive. Fx positive means fx lies above x-axis. Fx lies above x-axis in 0 to 3. So gx is increasing in 0 to 3. Now gx is decreasing means g prime x is less than 0. G prime x is equal to fx. So this means fx is less than 0. Now fx is less than 0 means fx lies below x-axis. Now from the graph I see that it lies below x-axis in the interval 3 to 7. So the function g is decreasing in 3 to 7. Okay. Now the last part of this problem, where does the function g have a minimum value? Where does g have a minimum value? This is very, very important. This is very, very easy also. So this is my third last problem. Let me do it separately. Let me rub it. So we have to just remember this result, that the function gx is increasing from 0 to 3 and decreasing from 3 to 7. So where does g have a minimum value? So to find out this, where does g have a minimum value, observe that g is, we have just in the last step we have already proved that g is increasing in 0, 3 and decreasing in 3, 7, right? So that means what? The function from 0 to 3, if you draw on the number line 0, 3, 7, from 0 to 3 the function was increasing, right? And from, it should be maximum value. Where does g have a maximum value? So from 0 to 3 the function was increasing, and from 3 to 7 it was decreasing. So clearly the graph of the function will be like this: from 0 to 3 it is increasing, and from 3 to 7 it is decreasing. So clearly from this graph it is clear that if this is so, then 3 is the point of local maximum. So from here, so clearly g will have a maximum value at 3, because the function is increasing from 0 to 3 and then decreasing. So where does g have a maximum value? At 3. So we will now be doing the last problem of note 8, that is for test 3. In my next lecture video I'll be doing a review of test 3 and also tell you the format of test 3. So this is the next problem. Use the fundamental theorem of calculus. Use the fundamental theorem of calculus to find the derivative of the following functions. Very easy. So let's take the first problem. Let's take gx as integral from 1 to x 1 by t cubed plus 1 dt. This is a very easy problem. So it's extremely easy. So you are given a function gx equals to integral from 1 to x 1 by t cubed dt. You are asked to find out the derivative of this function. So derivative of g means g prime x. So this means I need to take d dx of this function 1 to x 1 by t cubed plus 1 dt. Well then I have an integral sign and then I have a differentiable sign. So the integral sign and the derivative sign, they will cancel each other and I'll be left with whatever I had initially, but with this t replaced by x. So I'll be having my answer as 1 by x cubed plus 1. So these problems are extremely easy. So just your answer will be whatever was inside the integrand but with the variables change, right? So first you have to write down using fundamental theorem of calculus, or you can just write using FTC. Using FTC, g prime x is d dx of 1 over x 1 by t cube dt, which is 1 over x cube plus 1. So these problems are extremely easy. So if you are given a function like this, a function which has an integral sign, a function with an integral sign, and you are asked to find out the derivative of this function, you will understand that you have to use FTC or the fundamental theorem of calculus, and it is extremely easy. Your final answer will be just whatever was inside with the variable, whatever is the variable, change it to x. Your final answer is x cube plus 1. Let's take the next one. 2 gx is integral from 1 to x 2 plus to the power 4 to the power 5 dt. This is your original function. So its derivative using FTC, its derivative g prime x is simply d dx of 1 from 1 to x 2 plus to the power 4 to the power 5 dt. So I have an integral sign and a derivative sign. They will cancel each other. I'll be left with whatever I had initially. So I will have 2 plus x to the power 4 to the power 5 as my answer. So this is so it's very easy actually. So whatever was inside my integral, I have just changed the variable to x, and that's your answer. So let's take the third problem. gs equal to integral from 5 to s t minus t square to the power 8 dt. This is your function and you need to compute out the derivative. So g prime s will be dts of integral from 5 to s t minus t square to the power 8 dt. So you have an integral and then you are taking the derivatives, they will cancel each other. I will be left with whatever was inside, but with this t replaced by the variable of my original function. The variable of my original function was s. So when I write the answer, I just put whatever was inside just with t replaced by s. So it will be s minus s square to the power 8. And write using FTC. So it's very important and easy also, that just write using FTC and your answer will be just whatever was inside with the variables replaced by the variable of our original function. In this case, the original function's variable was s, so your final answer will be s minus s squared to the power 8. The last problem, 4. In this here your function was fx equals to x to the power 10 tan theta, right? So here using FTC, f prime x will be ddx of integral from x to tan theta. Differentiation and integration will cancel each other. I will be left with whatever was there, but with this theta replaced by my original variable, that is x. So I'll have tan of x. So I'm saying again, these sums are very important. Whenever you have a function which has an integral in it and you are asked to find out the derivative, you will understand that you have to use the fundamental theorem of calculus. Very easy. Just write using FTC and your final answer will be just whatever was inside the integral, that with this variable replaced by the variable of my original function. So here what I had tan x inside and the variable of my tan theta inside, and my variable of the original function was x. My answer was tan x. Here I had t minus t square to the power 8 inside and the variable of my original function was s. So I had s minus s square to the power 8. That is, I have just replaced this t by s. So that's how you do all the problems. So I have earlier sent you the solutions to it. Look at the solutions, revise them again and again, and then I think you should be well prepared for the test.